All right, guys. Hey, thank you for welcoming me to your class. I know you've been through a lot of changes this year. We're going to try to get through this year really strong, cover a lot of material. I'm going to try to get you ready for the exam as best as I can. We're going to run through this real quick. You can rewind this many times as you want. We get into biomes and different weather circulating patterns of the atmosphere and the water. I want you to think about um, what sort of what sort of things that the Earth has set in stone in terms of things that we really can't. They were predetermined, right? Like so our climates and everything. So if you read the little grape vignette at the beginning of the chapter, it kind of tells you that the biodiversity is pretty much determined by what latitude on the Earth you are, right? And we're going to talk about why different parts of the Earth are going to behave similarly, right? Why different latitudes are going to have very similar features, all right? Okay, so let's start here. So what is this word weather? What is this word climate? Weather is a short-term condition for the atmosphere of a local area, and we're talking about the lower parts of the atmosphere that we're going to talk about in a minute. These include temperature, humidity, clouds, precipitation, wind speed, and atmospheric pressure. Climate, on the other hand, is the average weather over a long period of time. Temperature and precipitation patterns are driven by these processes. So unequal heating of the Earth by the sun, we're going to talk about that in a second. What you should probably write there is the word tilt, right? So this has much to do with the tilt of the sun. Atmospheric convection currents. We're going to talk about rising and falling. This is adiabatic pressure. Rotation of the Earth. So if we didn't have rotation, we really wouldn't have a lot of transference of any heat or any of like the currents that you're going to see in a little bit, especially with Coriolis. Earth's orbit around the sun on a tilted axis. So this gives us the seasons right here. And it's going to give us the seasons. Over here, this is Coriolis. And atmospheric convection currents. This is rising and falling. So this is density properties, density and pressure properties of the air. And of course, the ocean currents. And the ocean currents, they carry nutrients, and they also transfer cold air, and they mix the surface water with the lower water. That helps. That has some interplay with some of the air currents. All right. So the troposphere. Let's talk about the different layers of the atmosphere. So the troposphere. So you're going to want to know the heights, right? These are all like really good trivia, multiple choice kind of questions. You want to make sure you know this. The troposphere is the densest, lowest. This is where weather happens. So this is a question that I'm going to definitely ask. Weather happens in the troposphere. This is the densest, lowest. It's going to be about 16 kilometers from the surface. So this is about 16 kilometers. Okay. The stratosphere above the troposphere has the ozone, which is the O3. O3. Okay. So that's a little bit less dense because of the property of air. The more dense it is, the more it's going to sink. That one's going to be between 10 and 50 kilometers. 10 and 50 kilometers. 10 to 50 kilometers. All right, this is going to be the mesosphere, thermosphere, and exosphere. And these you can kind of look up and look at the properties of them. We're going to look at some very interesting heating qualities of each one of these. So they have different molecules and different particles in them, which are going to absorb and re-emit heat very differently. All right, so look at this. You're going to want to study this here. You're going to want to definitely look at this and kind of see. Every time there's a bend in this heating and altitude curve, it's a double curve here. Here. So the temperature is increasing, right? It doesn't increase as you go up higher necessarily, right? I mean, it does here when you get into like the exosphere, thermosphere. But look here, the troposphere, temperature is decreasing as you get higher up, because we know if you go up to like the top of a mountain, right, the air is pretty cold, and that has to do with the sharing of kinetic energy and particles. But then look, as you hit the ozone layer, the O3 is going to absorb UV light really, really well. It's going to absorb it and re-emit it. It's going to get hotter here. And as you reach the stratosphere, there's a bend. So every time you see like a bend here, you're usually reaching a different boundary of the atmosphere. All right, unequal heating of the Earth. As the sun's energy passes through the atmosphere and strikes the land and water, it warms the surface of the Earth. But this warming does not occur evenly, right? Remember, we get all of our energy from the sun, right? We pretty much get all of it from there. All right, so let's talk about this idea of albedo. This is kind of cool. So different, we know that the sun is white light. The sun is white light, so it will reflect and absorb differently depending on the color of the object that it hits. So obviously something like sea ice, right, will have between 50 and 90% reflection rate. Water, depending on the angle, so you can imagine if you're looking straight at the water, if you shine a light straight into the water, if you've taken physics before, there's going to be not so much reflection, a whole lot of refraction going in, but not reflection right off the surface. As you make that angle of incidence increase and increase and increase, right? So if we do the angle of incidence here, I draw a normal line to the surface of the water here. The angle that I get in will be the angle I get out, right? So if I have a higher angle, I'm going to get more reflection, right? Asphalt, very little, as you would expect. It's black, it's going to absorb that stuff really well. Cropland, grassland, 10 to 15, 25%. Forest, a little bit less. Fresh snow, pretty high albedo, very white. Clouds, 10 to 90. I want you to think, why would this be between 10 and 90, right? Have you ever seen clouds that were kind of dark? You see other clouds that are really white, like this over here. It's a really horrible cloud, right? But you can see that the varying sizes of particles, right, especially as you get close to precipitation, are going to really change the amount of light that it either reflects or absorbs. All right, moving on. I'm going to pick it up a little bit now. So unequal heating of the Earth. There's a variation of the angle, right? This is huge. The variation of the angle that the sun's rays hit. Imagine you had your head in the sun, like you're in a car, right? And if the sun is coming down at you and it's hitting just like a little corner of your head, right? So let's say like there's an incident, beam coming in right here. It's hitting you right here in this spot of your head. This part's going to get really, really, really hot before anything else. But if I had like a different time of the day, right? Maybe like sunset. You can create it. It's fun. A lot of fun. And the sun's more even with like the horizon, right? You might get hit in this side of your head, and it'll be a little bit more even, right? So it really just depends. The amount of surface area over which the sun's rays are distributed. So if the sun is hitting a great angle through like the atmosphere, it's going to It's going to distribute that energy over a larger area, right? And each area is going to get a little bit less. Okay, and then we just talked about albedo before. All right. Air has four properties that determine its movement. We talked about that earlier. Density. We know about density. Less dense is going to rise. Denser air sinks. Water vapor capacity. This is important. Warm air has a higher capacity for water vapor than cold air. Okay. Adiabatic heating or cooling. This just kind of goes off of this density thing. So the cool air rising up is going to give it more space to kind of spread out, and it's going to cool down even further. At a certain point, it's going to start sinking, right? So as it sinks, the pressure of the atmosphere above it is going to compress the air closer together and warm it up. So just remember that the sinking is going to push the air closer together. The rising is going to make it spread out more and cool. Okay, adiabatic heating and cooling. This actually, I think there's some diesel fuel engines that use stuff like this. They just use pressure. They don't even need spark plugs. All right. Latent heat release. When water vapor in the atmosphere condenses into a liquid, the energy is released. Okay, when water condenses, the air warms and then will rise. So just think about it like this: like if you change state of like an object, you solid to liquid, liquid to gas, that sort of thing. Think about which state requires more energy. Right? If I'm going from a higher energy state, such as a gas, down into like a liquid, that energy had to go somewhere, right? So it'll go into the surrounding system, right? And if it leaves the surrounding system, that means that water is going to cool down even more, right? So just think about that. That's why you can walk over some sidewalk or area that had water on it that turns into ice. When the water on like a sidewalk turns into ice or something like that, the heat energy in that previously liquid water will now be above the pavement. It'll actually be a little bit warmer above it. All right, let's talk about convection currents. We are on the equator right here, so this is a Hadley cell. Hadley cells occur between 30 north and 30 south of the equator, so you need to know that. So 30 degrees to 30 degrees, right, with the equator. Right? So if we're looking at the Earth right here, so 30 above, 30 below, right? Okay, so you're gonna want to know these stages here. And this very special grouping of Hadley cells of this rising, see it's going to go cold as it goes up. As it reaches the limit, it's going to come back down and start heating up again. Get moisture here. Right? It gets dry as it goes up, moist, nice and warm as it goes down. But these special Hadley cells that converge on the equator are called ITCZ. They are intertropical convergence zones. Okay, so you need to know that. Okay, formation of convection currents. So this, hopefully we don't need to go into too great detail, but you are more than welcome to pause this and look at this a little bit more. Atmospheric convection currents are global patterns of air of air movement that are initiated by unequal heating of Earth. Okay, so Hadley cells, we just talked about that before. The convection currents that cycle 30 north and 30 south. Okay, intertropical convergence, we talked about that. And the most intense sunlight, so you're going to have a lot of convection currents there. And those IT CZs, they don't stay in the same spot because the tilt of the Earth ends up making the most intense sunlight kind of shift around a little bit. So it's not going to be right along the equator necessarily. You might end up having like a little bit of a wavy line that goes like this. Ooh, wavy line. Okay, cool. Okay, polar cells are at the very top. They're from 60 to 90, north and south. And of course you have feral cells, which are in between the two. And those three cells put together, they collectively act as like a little conveyor belt to move the heat up from the equator. So those three groups of cells are going to go, so I'm just going to draw the northern ones. So you got the Hadley, feral, and the polar cells. These guys right here are going to move heat from the equator up this way. Okay? They're going to move all together. Of course, we know that they actually cycle between those. They cycle within themselves, right? So we know that they're cycling here, and then it's going to cool down just a little bit, right, as you go further up. And then at the very top, you get cool air. But all that stuff, like warm heat energy, had to come from somewhere. And they all came from the Hadley cells in them. All right. Oh, Coriolis effect. This one's kind of cool. Coriolis effect. So the Earth's rotating, and because the equator is moving faster than the polar regions, currents that are moving north and south are going to get shifted. They're going to get shifted around. We'll do like a little activity to show this. But just kind of imagine that the Earth, right, is made up of concentric circles, right? So look at that, see? And what's happening to these circles of radius, or circumference even, as you get towards the equator, right? So the radii are getting much longer as you go downward and shorter as you go up. So imagine the circumference right here, right? The circumference right here, we'll call that circumference 1. And the circumference of the itty-bitty circle up here, we'll call that circumference 2. We know circumference 1 is obviously greater than circumference 2. Now, a really cool thing you might have learned about in physics is that, is it possible for any one part of the Earth, the solid portion of the Earth, to rotate any slower than another? Is that possible? I don't think so, right? So look here. So, no matter which part of the Earth I'm on, right, you have to concede that every single part, if this were like a record, like a solid record, that when they spin, the time it takes for a guy on the outside, make some little dots here, I'll show you what I mean. Purple dots, right? And we'll all right, now, buddy, I'm going to move this out the way for a second. Ah, where'd it go? It's gone. All right, we'll use it over here. Shapes, shape pen. Let's do some shapes. All right. Okay, cool. Perfect. All right, that'll work. Okay. Black dots for now. And we'll select that. I'm really going out of my way to try to prove a point here. Let's see. So if I rotate these guys at the same time, they will have to complete a circle in the same amount of time. But, there we go. The one on the inside, if you've ever been in band, will have to travel much faster if it's on the outside than if it's on the inside. You see that? So look here, the outside one looks like it's having to travel much faster, right? Crazy. Cool. All right, got that out the way. Okay, so that's the Coriolis effect. So you have this idea of deflection, right? So things that are moving from north to south latitudes, as they hit areas of the Earth that are rotating faster, they're going to deflect like that. If they're coming from north to south, they're going to deflect like that. If they're coming from south to south to north, they're going to go up and deflect that way. So they're going to deflect both in these directions, right? So like that. Bam. I might draw that out to the side, or you can look at this next picture here. All right, so here's a picture of that Coriolis effect. So see how they're deflecting inward as they reach the equator. All right, they're going the opposite way of the rotation of the Earth. Right, the rotation's from west to east, right? Which makes sense because the sun looks like it's going from east to west, right? So the sun only has apparent motion in the sky. It's apparent motion, right? Because the Earth is rotating the opposite way, right? So that's an easy way to remember. The sun comes up in the east, goes down in the west because the Earth's going the opposite. So if these guys are trying to come down this way, they're going to deflect the direction of the Earth's rotation. It's Coriolis effect. And snipers actually have to take this into account for things that are really, really far away, or you're firing missiles or rockets or anything like that. Okay. So that's more of the Coriolis effect. Okay. So the big picture of all of this is that our winds will circulate through convection, which we talked about in those Hadley cells, and the Coriolis effect. Let's move on. Okay, so here's a picture of that. You may want to look at this. Cool, cool, cool. These are these intertropical convergence. And see how it kind of is wavy? Yep, that's because of the Earth's tilt. All right, guy. Okay, so here's the tilt, 23.5 degrees. That's very important. If we didn't have a tilt at all, we wouldn't have seasons. Okay, we would just get the same amount of sunlight everywhere at the same time. We'd have a hard time regulating temperature, or at least having differences in temperatures. When the northern hemisphere is tilted toward the sun, this is important. Imagine you put your head, you put like your forehead towards the sun, your big old forehead, you put it into the sunlight. It's going to get hotter than the back of your head or your chin, right? The southern hemisphere is going to be colder, right? So that's why our seasons are opposite. So our seasons are opposite in the hemispheres. North-south hemisphere. I'm just going to put hemi, okay? Okay, so here you can kind of think about this. So here's our spring, here's our fall. These are the March and September equinoxes. Look here, we're getting kind of a equal amount of sunlight. Not really too many extremes here. You can see the northern hemisphere is pointing directly into the sunlight here, so this is going to be like our summer. Okay. Ocean currents. Let's talk about currents real quickly. The ocean currents are a combination of temperature, gravity, that's important, right? Prevailing winds, the Coriolis effect, and location of continents. So this is something that you're going to do comparison of these differences and similarities. Okay, so we have temperature, air currents were the same, atmospheric currents were the same, right? And to a certain extent, there is some gravity with air as well, because air is not just like this invisible vapor, right? It's made up of the elements, right? And heavier ones are going to be pulled down more than the lighter ones will. Winds, right? So winds are controlled by winds. Oceans are controlled by winds. The Coriolis effect, you see how the Coriolis effect also affected the atmosphere, right? And the location of the continents, this one is a difference right here, right? The continents getting in the way will change the path of the ocean, right? So this one is location of the continents. This is a difference. Okay? Water, like air, expands and rises. These are important right here. Gyres right here. These circulate the surface water. They're going to circulate the surface currents. They go in a clockwise direction in the northern, and a counterclockwise in the southern. Okay, cool. Okay, so here's a picture of that. You have this in your textbook, your wonderful, wonderful textbook. Make sure you're doing these. Make sure you're doing your strive for fives as well. See the clockwise up here, counterclockwise in the south, right? And what were these blue lines? And we'll get to those in a second. These are upwelling. We're going to talk about upwelling. Here is upwelling. So surface currents separate from one another. So as you separate and deviate from like continents over here, you see how there's like some separations. Here, just go around continent here, go around this island here. This separation right here is going to give room for water from below to fill the space, right? If I, open my fingers, right? it lets air that was underneath my fingers kind of flow through, right? So that's what these gyres are kind of acting like. Okay? That's very important because upwellings are going to cycle nutrients from the bottom, colder water. It's going to bring, primary producers, and then that's going to bring small fish, secondary consumers, tertiary consumers, all that good stuff, right? So what do you think would happen if we disrupted these currents, right? If we mess with these currents by changing the way that weather patterns work, if we don't have changes in extremes in temperature, then these currents aren't going to flow, right? They're not going to flow. They're not going to create these upwellings. We're going to have like destruction of our trophic pyramid, right? So you can kind of think of ways to extend these ideas to that. Okay, thermohyaline circulation. So this is kind of going off of the bottom waters as well. So thermohyaline hyaline circulation. It's an oceanic circulation that drives the mixing of surface and deep water. That's important. This is crucial for moving heat and nutrients around the globe. Thermohyaline circulation appears to be driven by surface water that contain unusually large amounts of salt. So this is going to be another difference in water circulation or ocean circulation, ocean current circulation. Okay? Some of the water that flows from the Gulf of Mexico to the North Atlantic freezes and evaporates, and the salt that remains behind increases the salt concentration of the water. So evaporation is very, very important. And you're going to see here that the evaporation, what happened to my pen? You did that, okay? The evaporation is going to increase the density of water. So the density is going to increase as it evaporates. And it's because the salt is staying behind, right? Cold, salty water is relatively dense, so here it is. So it sinks to the bottom. So denser things sink, mixing with deeper ocean waters. These two processes create the movement necessary to drive deep, cold current that slowly moves past the Arctic and northward to the North Pacific Ocean. So think about what would happen if we did something to the water to decrease the salinity. So what happens if we decrease the salinity, right? And what do we mean by that? If you have really salty water, like you put too much salt in a guacamole, you'd have to try to increase the amount of avocados, right? But if you increase the amount of avocados, you're changing the salinity of that entire thing, right? So we only have a certain amount of salt that we can just introduce all at the same time. So look what's going to happen here. So here's the mixing of surface and deep waters for salinity, right? The answer to that other question was you're not going to have sinking, right? That's the short answer. I was kind of waiting for a more dramatic thing, but that's pretty much it. The heat transport. Ocean currents can affect the temperature of nearby land masses. So England's average winter is approximately 20 degrees Celsius. Warmer Newfoundland, Canada, which is located at a similar latitude. So similar latitudes are going to have similar weather because of the amount of sunlight they're getting, the angle of the sun. Okay, this is ENSO, El Nino Southern Oscillation. ENSO is what they call it, ENSO. And it says that in your book as well. No, I'm not calling it. Every 3 to 7 years, the interaction of the Earth's atmosphere causes the surface currents of the tropical Pacific Ocean to reverse in direction. This is important. This usually happens around Christmas. Right? Usually happens around Christmas. Oh, what happened? Come back. So notice here the trade winds are kind of going this way. You get surface water and cold deep water circulating in. But look what happens if the trade winds switch. They go from being westerly to being easterly. Look what's going to happen. This is the east coast of South America. So now this hot water is going back. Am I able to get cold water upwelling here? No, I am not. So that's going to affect lots of things. Think about how that would affect the biodiversity here. Think about how that's going to affect the producers, and how it's going to affect the trophic pyramid. Think about how it's going to affect commerce and industry, right? Jobs, all that good stuff. These are things, El Nino is, of course, something we really can't do much about, right? This is just something that happens. But, we can think about other things that we do that kind of change these patterns as well, right? So the trade winds near the South American continent weaken. It allows warm equatorial water to move eastward toward the west coast of South Africa. So I think I said that wrong. Sorry, it's the west coast of South America. I think I'm saying Africa. The movement of warm water towards South America suppresses the upwelling. It reduces fish populations. These periodic changes, currents, are called the El Nino Southern Oscillation, or ENSO. Okay. Rain shadows. Talk about rain shadows. You know about rain shadows. I'll break it down pretty easily. It's not really that hard. When air moving inland from the ocean contains a large amount of water, uh, meets the windward side of the mountain, the side that it has the incident winds called windward, it rises and begins to experience adiabatic cooling. And remember that as air rises and separates, it starts to cool. Okay? So water vapor condenses as it cools. So it's going from a vapor to a liquid state, right? So it's losing some of its energy, right? So it's becoming cooler. It forms precipitation. So it's raining on the windward side of the mountain. The presence of the mountain range creates large amounts of precipitation on the windward side only. That dry air goes to the other side of the mountain, the leeward side, where it descends and experiences higher pressure. And we know from adiabatic um, pressure systems that it's going to heat as it gets higher pressure. Okay, so now this air is really, really warm, and it's going to be hot and dry on the other side. We call that a rain shadow. Okay, so this is what it does. And the really easy way to remember this is that with regular adiabatic cooling, like Hadley cells, if you didn't have this mountain here, you would have hot air rising, right? You'd have hot air rising. And as it reaches the top of this thing, right, what's it going to do? It's going to become cool air, right? It's cool air up here, but then it starts to fall, right? And it cycles through, and it becomes hot again, right? But what's happening here is basically this mountain's getting in the way, right? This mountain's getting in the way. So this hot stuff is releasing all of its cool rain and everything. It's just coming back down as hot. It's not getting a chance to cycle back through. So that's how you can end up with very, very different climates on both sides of this. Now, think about the different ecosystems you're going to have on both sides, right? You have very, very different things. We talk about biomes. You can have something totally different on one side of the mountain, the windward side, and the leeward side. But imagine if you came in and just like removed the top of this mountain from mining, right? Think about what that's going to do, right? So that's a cause, that's a human effect on the environment that you can think of. Damage to the ecosystem, right? So think about that. And that's it for right now.